Hi everyone. In this video we're going to look at some convergence tests for determining the convergence of an infinite series. So in the previous video we looked at determining convergence or divergence of an infinite series using the definition of what it means to converge or diverge, which focuses on partial sums. Here we're using tests which won't tell us what a series does or does not converge to or diverge, but instead it just tells us if it converges or diverges without telling us what it converges to or if it diverges. Okay. So the first example is called the nth term test. So here is our infinite series, and we're going to focus on the terms in that series. So we're going to focus on the 1 minus 1 over 2 to the I, and we're going to take the limit of that as n goes to infinity. Okay. As n goes to infinity, 1 minus 1 over 2 to the n is going to be 1 because the 1 doesn't change as n goes to infinity, and 1 over 2 to the n goes to 0 because the numerator stays the same and the denominator grows larger and larger. Okay. That limit is greater than 0. So the nth term test, which is to take the limit of the nth term, tells us the series diverges because this limit is greater than 0, and so effectively we're adding up infinitely many terms that are greater than 0, and so we get an infinite summation. So we say that the series diverges. Okay. Now we're going to do an example using the limit comparison test. This is a more complicated example. So I'm adding the summation I equals 1 to infinity, 5i cubed plus 1 divided by I cubed times 2 to the I. So the terms in this series all look like this. For the limit comparison test, I want to compare this to something similar to a sub n, but that I can sort of get a better handle on. And what I notice is that if n is really large, the plus 1 doesn't matter, and the n cubes don't matter. All that really matters is the 2 to the n. Okay? So if n is really very large, 2 to the n is so much larger than everything else there that I can compare this to 1 over 2 to the n, and I like this because this will give me a series that looks like the geometric series that we've looked at in previous videos. Okay. So for the limit comparison test, I'm going to take the limit of a sub n over b sub n. So I divide the a sub n terms by the b sub n terms. When we do that, the 2 to the n's cancel. And then as we take the limit, we're just going to be left with the 5. Okay, so the limit of a sub n over b sub n equals 5. Because I'm getting a nice finite number, this means that they grow at the same rate. They have comparable growth rates. And so if one series converges, the other converges. Now the summation of the b sub n converges because it's a geometric series, and so s, which is the summation of the a sub n's, also has to converge. So in the limit comparison test, you might start out with a fairly complicated looking series, and you want to compare that to something simple that you already know the convergence of. So in this example, I compared this complicated series to a geometric series that I knew converged because we've done it before in a previous video. And because their growth rates are the same, and because the summation of the b sub n's converges, I knew that s had to converge as well by the limit comparison test. All right, for the next test, we're going to use the ratio test. Part of the problem with the limit comparison test is you have to have two different series for that comparison. In the ratio test, you get to compare a series to itself. So I still want to look at the nth term, and here the nth term is 1 over n factorial. And then I need to take the limit of a sub n plus 1 over a sub n. So we're comparing one term of the series to the term that comes immediately before it, and taking the limit as n goes to infinity. When we simplify this, a sub n plus 1 is 1 over n plus 1 factorial. A sub n is 1 over n factorial. When we divide fractions, we flip and multiply, and so that will give us n factorial over n plus 1. But with factorials, we get a lot of nice cancellation, and so that will be equal to the limit as n goes to infinity of 1 over n plus 1. And that equals 0, which is less than 1, and the ratio test tells us that as long as this limit, as long as the limit of a sub n plus 1 over a sub n is less than 1, then the series converges. So this series converges by the ratio test. So the ratio test works really well if you have series that will give you lots of nice cancellation when you divide one term by the previous term, okay? If that's not the case, this might not be a great test, but with something like factorials, that works really well, okay? So this converges, this series converges by the ratio test because we got a limit less than 1. Okay, for our last test, we're going to do the integral test. So here's a series. It's not a particularly complicated series. It's the summation I equals 1 to infinity of 1 over I cubed. And this integral test means we're going to compare this series to an integral. So in particular, I'm going to compare the summation of 1 over I cubed to the integral of 1 over x cubed. And here we have a graph of the function 1 over x cubed, and our infinite series looks like this left box Riemann sum. Okay? And we can see that all the boxes in this left box Riemann sum are below the curve. And so the summation of the series is bounded above by the area underneath this curve. So that's why we're comparing this series to this integral. Okay. The antiderivative of 1 over x cubed is negative 1/2 x to the negative 2. We're evaluating this using a limit because it's an improper integral, and so we had to change that infinity to a limit. If we evaluate that limit with the limits of integration between 1 and b, we get 0 plus 1/2, which is 1/2. So the area underneath the curve between 1 and infinity is just 1/2. And that gives us an upper bound on the infinite series as well. And so we could conclude that the series also converges. Okay, so that's 4 examples of convergence tests. There are actually far more convergence tests than that. But hopefully that gives you a feeling for how we can use convergence tests to determine the convergence or divergence of an infinite series. What I want to point out, though, is that all the infinite series we looked at in this video had terms which are positive, okay? We always had positive terms that we were dealing with. In the next video, we're going to talk about alternating series where some of the terms are positive and some of the terms are negative. And so I'll see you in a little bit for that video.